isotopes of hydrogen are protium and deuterium. Protium has an atomic mass of 1.0078 atomic mass units and represents 99.989% of hydrogen atoms. Deuterium has an atomic mass of 2.0141 AMU and represents 0.011% of hydrogen atoms. Calculate the average atomic mass of hydrogen. Well, what we do is we take each isotope's mass, so in this case the first one, the 1.0078, and we multiply it by its percentage abundance converted to a decimal. So that's 0.99989, and we get a value there. And we do the same thing for the other isotope. So the other isotope is 2.0141, and we multiply that by 0.00011, and we get this very small number. Then you take those two products and add them together, and if you've done it correctly, you should get the same average atomic mass as you see on the periodic table, or at least something very, very close to it. And we do. So that's how you calculate the average atomic mass for an element. Now sometimes you may have a problem like this, where it says that gallium has two main naturally occurring isotopes. Gallium-69 has a mass of 68.926 AMU and an abundance of 60.108%. What is the mass of gallium-71? So it looks like we have a puzzle basically here, because we're not being asked what's the average atomic mass of the element. We're being asked to essentially work backwards and find the mass of one of the isotopes. You can set the problem up the same way. What I would do is I would start by writing down this number, the 69.723, and you might be wondering, where in the world does that number come from? Because that's not in the problem. Well, that is, from the periodic table, that is the average atomic mass of that element from the table, 69.723. And then I'm going to take this other isotope, the 68.926, and multiply it by its abundance, the 0.6108, and I get this number. And now I know that there should be some other number in here that I would have, so I'm going to subtract. So I take the 69.723 minus 41.430, and I get 28.293. Now that number is going to be the product of the percentage abundance of the other isotope times its mass. So I'm slowly working backwards and getting back to that original number. Now, what is the percentage abundance of the other isotope? Well, it has to be 39.892%. Now, how did I get that number? Well, the problem says that we have two naturally occurring isotopes here. And if we have two isotopes and one is 60.108%, well, your 2% have to add up to 100, don't they? So just subtract from 100, and that's how you get this other percent, or subtract from 1 in this case. So now we can divide. We just take the 28.293 and divide by 0.39892, and we should get the mass of the other isotope, which is about 70.925. Now, occasionally they do ask this type of problem on the AP exam. Sometimes they don't, but this is a very good skill to be able to calculate the mass of a missing isotope. Now, you might wonder, how do we get these numbers? How do we figure out the mass of an isotope? Because you can't really take an atom, an individual atom, and place it on a little teeny tiny scale and figure out its mass. That would be ridiculous.
Gravity Defier for life. IMS for life.
This Charmin Ultra Soft Smooth Tear has wavy edges.
It's no ordinary square. Charmin Ultra Soft Smooth Tear has wavy perforations that tear so much better.
ridiculous. Well, we have an instrument that helps us to analyze the relative abundance of isotopes in a sample. This is how we get these values. This is called a mass spectrometer, or sometimes a mass spec for short. And if we take a super purified sample of zirconium and stick this into the mass spec, we can get a little graph here that shows us the analysis of zirconium. So we have the relative abundances here. It shows each little bar on the graph represents a different isotope. And the height represents the relative abundance in percent. And then how far left and right it is shows the atomic mass of each isotope. So we can get some very valuable data out of this. So for example, if we were to ask how many isotopes of zirconium are represented on the graph, I hope that you could count that there are 5 little bars here, so that shows that there are 5 isotopes here. And if the question was, which of the isotopes is the most abundant? Well, the one that has the tallest bar, so that would have to be zirconium-90. It's got something like maybe about 52% abundance there. And the least abundant would have to be the shortest bar, so that would be zirconium-96, something like maybe 2 or 3% would be there. If it says estimate the abundance of one of these isotopes, well, zirconium-92. Now, zirconium-92, of course, would have to be right here. It's labeled. It's also right at the 92 mark there. What is the abundance? Well, it's between 10 and 20. It looks like it'd be about maybe 17, 18%. So you should be able to answer questions like this by looking at a mass spectrometer graph. Now, let's say we have a question like this. This is a sample multiple choice question, and it says, which of the following elements has the mass spectrum represented here? And we have this mass spec graph, and we have a choice of 4 elements. Now, you will need a periodic table in order to answer this question. You're going to have to eyeball basically the center of this. Where is the approximate weighted average of all this? We have a couple graphs that are taller and smaller than others, but it looks to me like the average is somewhere around 96. That's what I would say. So what I'm going to do is look at my periodic table and find an element that has an atomic mass that's very close to 96. And as I look on the table, I see that molybdenum is very close to that, 95.95. So I'm going to say the answer is choice B. Now, the only other answer that's even possibly reasonable is niobium, Nb. But if I look at the table, it has an atomic mass of about 92.91, which that's not really in the center. As you eyeball this, try to get somewhere in the center of that weighted average. That's why molybdenum is the correct answer for this. Let's try one more multiple choice question. Let's imagine that we have 2 different ionic compounds that each contain only copper and chlorine. Both compounds are powders, one white and one brown. An elemental analysis is performed on each powder. Which of the following questions about the compounds is most likely to be answered by the results of the analysis? And we have different questions here. What is the density? What's the formula unit? What's the chemical reactivity? Which is more soluble? Well, if we're doing an elemental analysis, then what we'll be able to find out will be how many atoms of each element are in the compound. So that would be choice B. What's the formula unit? For these other things like density, reactivity, solubility, the best way to determine those things would be not with an elemental analysis, but rather by carrying out those actual processes in the laboratory. My name is Jeremy Krug. I hope you've enjoyed this video and learned something from it. Please give me a thumbs up, or even better, subscribe if you enjoy this content. And I hope you do very well on Unit 1, Section 2 of AP Chemistry. In Unit 1, Section 3, we're talking about chemical formulas and where they come from. Now, all the way back in the 1700s, We have this French chemist named Joseph Proust who found that different samples of a chemical compound are always going to have the same composition of elements. And he was able to figure this out by analyzing different samples of the same compound. He called this the law of constant composition, sometimes called the law of definite proportions. And we find that this is true today. We find that, for example, if you have a sample of water, it doesn't matter where that water comes from, it's always going to be about 11% hydrogen and about 89% oxygen. Doesn't matter where that water comes from. Now, at the same time, if we take other compounds like sodium chloride, doesn't matter where the sodium chloride comes from, as long as it's a pure sample, it's going to be about 39% sodium and about 61% chlorine. So this is the constant composition that we see for these chemical compounds. Now, John Dalton, a British chemist in the early 1800s, basically was able to take some ideas that other previous scientists had thought about and come up with, including Proust and some others like Antoine Lavoisier, and explain the way that chemicals behaved by the existence of atoms. And so he came up with this atomic theory to explain why chemicals and substances behave the way they do. This had 4 statements. The first statement of his atomic theory was that all elements are composed of atoms. At the time, it was a very revolutionary thought to say that there were atoms. This was not something that people really thought of too much. A second part was that atoms cannot be created or destroyed in a chemical reaction. And we know that that certainly is true today. The third part was that atoms of one element are different from atoms of other elements, and that all atoms of an element are identical to each other. Now, if you watched the last video in Unit 1, Section 2, we know that the second part of that is wrong. We know that there are these things called isotopes. You can have different varieties of an element, like we saw the 3 isotopes of hydrogen. They're not identical. So that part of his atomic theory was wrong. But the first part of it is certainly correct. Atoms of hydrogen are going to be completely different from atoms of oxygen, on the other hand. The fourth part was that all compounds have a fixed ratio of atoms of elements. And that sounds a whole lot like the law of constant composition that we just saw from Joseph Proust. Now, when we take a compound, we have learned already how to calculate the mass percent. So just as a very quick example, in the case of caffeine, there's its formula. We just take each number of atoms there, multiply it by its atomic mass. We have 12 for carbon and about 1 for hydrogen and about 14 for nitrogen and 16 for oxygen. And then we add those values together and we see that the overall molecular mass of caffeine is about 194.0 AMU. And to find the percent mass for each of those individual elements, we just take the individual products for each element and divide by the total. So carbon is 96 divided by 194, which is about 49.5%. And hydrogen is 10 divided by the total, about 5.2%. And nitrogen, the same way. Oxygen is the same way. So this is the percent mass. Now, is it possible for us to go in the other direction? Is it possible for us to take these percents and work backwards and get back to a formula? Well, I think it is. Now let's see how we...
$6 never tasted so good. IHOP's Breakfast Faves combo is now just $6. Featuring IHOP's world-famous buttermilk pancakes, crispy hickory smoked bacon, and 2 eggs cooked to order your way. All for just $6. Part of the new $6 House Faves menu.
Make every wash count.
Do that. Let's take those percents that we just calculated, and we're going to go backwards. We're going to determine the empirical formula of caffeine. Now, the way that we do this is we take those 4 or however many percent values we have given to us, and we write them down. And notice this is percent by mass. And so since it's percent by mass, I can call those percents gram values. So it's like if we had a sample of 100 grams of caffeine, 49.5 grams would be carbon, and 5.2 grams would be hydrogen, and so forth. Now, just like in any of these conversion problems, a good first step is always to convert to moles, isn't it? That was one thing we saw way back in section 1 of Unit 1. So we're going to take all these gram values and convert them to moles using their individual atomic masses. And so we just do that. We have the mole values, so 4.125 moles and so forth. Now, once we have moles, we're going to divide each of those by the smallest of those mole values. So as I look at those 4 mole values down here, I see that the smallest one is 1.031. So I'm going to divide all of those by the 1.031. Now, when I do that, I get a number of 4, or very close to 4 for carbon. I get very, very close to 5 for hydrogen. I get very close to 2 for nitrogen, and I will of course get 1 for oxygen. These, the 4, the 5, the 2, and the 1, represent the subscripts. So we have C4, H5, N2O. So that's the empirical formula of caffeine. Now, you might be thinking, hang on a second. We saw the formula for caffeine on the last slide, and this was not it. So what's the deal here? We actually don't have the real formula. This is what's called the empirical formula. And the empirical formula is a formula for a compound that represents the lowest common ratio for atoms of each element. It's kind of like a formula that's been reduced down to lowest terms. It's like, for example, if we have glucose that has the actual or the molecular formula C6H12O6, if you reduce that down to lowest terms, its empirical formula becomes CH2O, because you can divide each of those subscripts by a factor of 6. So CH2O is the empirical formula. Or this here, we have this compound called hydrazine. It's N2H4. That's the actual or the molecular formula for that compound. And we can divide both of those subscripts by 2 and make the empirical formula NH2. Now, sometimes the molecular formula is the same as the empirical formula, because water actually is H2O, but you can't reduce that down anymore, so its empirical formula is also H2O. In the case of tetraphosphorus dicoxide, P4O10, we can reduce that down to an empirical formula of P2O5, can't we? So we have a molecular formula and we have an empirical formula, which is in the lowest terms. So is there a way to go from empirical formula to molecular formula in the case of our little caffeine problem here? Well, yes, there is. And that little nugget of information that we need in order to make that last conversion is the molecular mass of the substance. So here's the empirical formula of caffeine that we just calculated. And it says that the molecular mass of the caffeine is 194.0. With that, now we can go to the molecular formula. And the way that we do that is we take the empirical formula that we just calculated and we add up the atomic masses of all these, and we find the molecular mass of this object here. So 4 carbons, that's 12 apiece, 48. We have 5 hydrogens at about 1 apiece, that's 5. 2 nitrogens at 14 apiece, that's 28. And 1 oxygen, which is 16. That adds up to 97. Now, the molecular mass is 194. So we divide the molecular mass by the empirical mass that we just got. And we find that the ratio there is 2. So what that means is we have to multiply the empirical formula by 2. And when we do that, multiply all those subscripts by 2, we get the C8, H10, N4, O2. That's the exact same molecular formula that we had way back at the beginning of this problem. So that's how you can go from the percent by mass data backwards to the empirical formula and even the molecular formula. So that's actually a very neat little calculation to do. Let's try one more example here. We're going to take a compound, this time with nitrogen and oxygen, and it has 25.93% nitrogen and 74.07% oxygen. Let's find the empirical formula. So once again, we have those 2 gram values. And first thing that you want to do is convert the gram values to moles. So we're going to divide nitrogen by about 14 grams in a mole and oxygen by about 16 grams in a mole. And when we do this, we get about 1.852 moles of nitrogen and about 4.629 moles of oxygen. Now what's the next step? We have to take both of these mole values and divide by the smallest, or the smaller of those 2 in this case. So that's 1.852. So of course this first number is going to be a 1, and when I